Hi, my name is Sarah Gao. I'm a sophomore here at Lehigh University studying chemical engineering. Over the past year, I've been doing research in Professor Rachmanis's lab studying organic electrochemical transistors. Organic electrochemical transistors, or OECTs, are a bioelectronic device that can act like traditional transistors and amplify current. These devices are made up of a source, drain, and gate electrode. The source and the drain electrodes are connected through a polymer channel, while the gate electrode is immersed in an electrolyte that is covering the polymer. Typically in OECT operation, a voltage is applied at the gate electrode inside of the electrolyte, and this voltage drives redox reactions that occur between the polymer and the electrolyte. And this is a process called electrochemical doping, and it causes a current flow between the source and the drain. And that's how this device is able to amplify a small input into a larger current. In my research, we are focused on studying the polymer carboxyl alkyl polythiophene. This polymer is unique because it contains it has both hydrophobic and hydrophilic qualities. Typically a challenge that we see with OECTs and the associated polymer is that since this polymer is covered by an electrolyte containing water, it will swell and have shifts in the structure of this polymer. And eventually this makes the polymer less stable and it will degrade more easily and it will not have consistent measurements. And so with our polymer that we're studying, which is also called P3CBUT, this polymer is kind of able to withstand the changes from being covered in an electrolyte because of its hydrophobic spacers. So in our measurements, or in our studies, there are two different kinds of samples that we use for different kinds of measurements. The measurements that we used were output curves, transfer curves, and cyclic voltammetry. And so for the output curves and the transfer curves, the samples that we prepared were an interdigitated OECT. And for the cyclic voltammetry or testing the electrochemistry, we would use a conductive glass sample. And so for both of these samples, there would be constructed by having the water-soluble version of the polymer, and it would be spray coated onto each platform. And after being dried, these samples would undergo an acid treatment with a PTSA wash as well as a methanol wash, and this would create the hydrophobic spacers. And so for testing, we initially started with cyclic voltammetry or testing the electrochemistry of the polymer. And so to do that, we would take the conductive glass sample and connect it to a potentiostat with a counter and reference electrode. And so our sample would act as a working electrode, and all three would be immersed in an electrolyte. And in our case, we used the electrolyte KCl, or potassium chloride, at 0.1 molar. And so for cyclic voltammetry, there's a voltage sweep going from negative 0.6 to positive and then back to negative 0.6. And then the resulting current from that voltage sweep is measured and analyzed. And so as we can see in the graph, there is current being conducted in the positive range of the voltage, indicating that this is a P-type like conducting polymer, and that this polymer is also able to conduct and act and be like feasible as the polymer of choice in an OECT device. And so for our transfer curves and output curves, these are both measured in similar ways. voltage at the source is held constant while the gate voltage varies, and then the resulting drain current is measured. And so for our output curves, the source voltage is incremented. So each of these lines is the resulting drain current as a result at different source voltages. And so output curves are used to determine the optimal source voltage to take measurements at. And so as we can see on the graph, the output curves reach a maximum where increasing the source voltage doesn't result in any more increase of the drain current. And we reach that point at a source voltage of minus 0.6. And so we use this source voltage in the transfer curve. A difference between the transfer curve and the output curves is that the transfer curves sweep from 0 to minus 0.8 volts back to 0. Of course, with the source voltage being held at minus 0.6. And something that we're able to do with this transfer curve is plot the transconductance. And the transconductance is essentially the derivative of the drain current with respect to the gate voltage. And looking at the transconductance curve, we can see that we reach a peak transconductance at around a voltage of minus 0.5, determining which shows that that's the most effective range for this polymer. And so overall, we've discovered that this is a very feasible polymer, and some future works that we're exploring is looking at different preparation types, as well as comparing this to different polymers. And even more long-term, OECTs have a wide range of applications that can range from bioelectronics to